So everyone can hear me. Welcome, everyone. Welcome to Harvard University Center of Mathematical Sciences and Applications, CMSA Quantum Matter Seminar Series. Today, we are very honored to have Vishik, Professor Ina Vishik from UC Davis. And this is also a program on this strongly correlated quantum material and high temperature superconductors. Okay. So next. As I say, this will be a series. The second speaker about the third talk. If you were here yesterday, Subir gave his second talk on this. The second, Ina is the third talk on the series. The second speaker on the strongly correlated quantum materials and high temperature superconductors. Okay, and Professor Ina Vishik studied a PhD at Stanford University under Professor Zhixun Sen. And then she went to MIT, did his postdoc as a postdoc fellow. That's where actually I met her at MIT. And she currently is a assistant professor at the UC Davis. And her research has contributed to understand the emergent electronic phenomena in quantum materials and unconventional or high temperature superconductors, correlated electronic systems, topological materials, and 2D specific 2D materials using this ARPES, angular resolved photoemission spectroscopy, and the time resolved techniques, such as the picoseconds, 10 to the minus 12 seconds, study the life of superconductor. And there's a very nice talk she gave at MIT a few years back, and you can watch. These advanced materials hold promise and will be revealing emergent phenomena, elucidating the interactions in many body systems, enable tomorrow's electronics and energy resources. As many of you right now is in the lockdown time, so when you come to seminar, there's not much interaction with the speakers. The reason I try to say a bit more is try to fill in this gap. You may still feel a bit social and try to understand, speakers. And the next few slides, I'll just be very quick. Ina actually contribute more widely than just research. He also outreach to general public by broadcasting science ideas, communicate with people. Actually, she answered many more questions about science-related questions, and she actually explained very well and for wide topics related to condensed matter, quantum matter. You see, she actually posts more than 1,000 answers, and many of them are really excellent. I read many of them and benefit a lot. For example, she explained the recent development and recent finding of this nearly room temperature superconductor of this resonant superhydrate superconductor at this 260K. And there's some nice explanation and give a credit to these papers. And more than that, she's also an avid enthusiastic marathon runner, and she also gives advice to people who run marathon in a very scientific way. And you can read her post. Sorry about that. In addition, she also very generous to answer questions about personal relationship, and people should not be shy. For example, if female interested in dating intellectuals in Boston, she gave advice like, if you want to find them, like single professor in Boston, they will usually be in his office late in the evening and on the weekend. So they are very nice advice she gave. And she also gave a scientific reason, for example, why people thought that women might desire diamond. There is a scientific reason because diamond actually becomes superconduct. And when they are doped with boron, actually it can predict that it can be even higher temperature superconductor. So there are many benefits like that. And this is just a very short summary on many things she answered and very patiently. And today, as her seminar will start in 1 minute, please feel free to ask questions, and I'm sure that Ina can answer very nicely. But please have some self-discipline And please post on chat if you're not sure when to ask. And we hope the environment will be friendly and constructive conversation between us. Okay, so let's welcome Professor Ina Vishik from UC Davis. She will be speaking about universality versus material dependence in cuprate ARPES studies of the model. Sorry, my screen is a bit small. Of the model cuprate on this Mercury 1201. And let's welcome Ina. Thank you very much.
All right, thank you very much for that introduction, Juven. It looks like I'm a co-host, so I'll go ahead and share the screen.
Yes, please.
All righty. And let me put this on the slideshow mode. All right. Do you want video on? Do you want my video on? Let me go ahead and do that so it's more personal.
Thank you.
All righty. Okay. So thank you again, Juven, for this this invitation and the really warm and friendly introduction. And also thank you to everyone in the audience for accommodating the late West Coast start time. I really appreciate that as well. Today I'll be sharing my group's recent results on Mercury 1201. And beyond that, I want to discuss something that I've been thinking about a lot in recent years, the idea of universality versus materials dependence in the cuprate. So this is something that really came to the forefront with the advent of the iron-based superconductors, where there were all these different compounds and no one could keep track of which one was which. Whereas in the cuprates, there's like 3 or 4 of them that everyone studies. However, in cuprates, there are also like 200 ones that have been discovered, but we have not studied the majority of them, and maybe the answers we're looking for are lurking in some material that has been seldom studied. I have the chat window open right now for you guys. If you want to type questions into the chat, or if you just want to type into the chat, I have a question, I'll be able to see it right away. And you're also welcome to just shout out your question. And what else? Oh, and also sometimes I accidentally move away from my microphone. So if you can't hear me for whatever reason, just go ahead and pipe up as well and let me know about that. Okay. So, whoops. Okay, so this is going to be a talk about my group's work on cuprates, but before I get into that, I want to introduce my group and highlight some of our other work. So those of you who've known me for a long time might only know me for studying cuprates, but my group actually has a broader materials portfolio these days, broadly looking at 2D and topological materials in addition to correlated and superconducting ones. So my group, we do both ARPES and ultrafast optics experiments. On the ARPES side of things, we have a lab-based system, but we also do experiments at synchrotrons. And then with ultrafast optics, we study dynamics of materials in a very versatile way that's accessible to all kinds of compounds, including ones that don't cleave. So some of our recent highlights have looked at electron doping-induced phase transitions in tungsten ditelluride, a nodal line semimetal, and also ultrafast optics and decay dynamics of a topological insulator compound. And despite this being a very ubiquitous material, just like the cuprates, there is still more discoveries to be made, even with established experimental techniques. So these are some of my current and recent group members. So my postdoc, Antonio Rossi, recently went on to LBL. Two students on the ARPES side are Sudhir and Matt, and Sudhir is the one that participated on this project. There's a standing wave X-ray effort in my group. That's a whole nother story with Enrique Martins leading that. And the ultrafast optics is in the purview of Adam Gross. With that, let me get into my actual talk. So the outline is as follows. So in the introduction, I'll discuss some of the avenues of materials dependence among cuprates and give a brief introduction about ARPES. When Duban invited me, he told me to don't be shy about giving a lot of introductory material, and I think I've taken him up on that offer. And then I'll get into our results on Mercury 1201, which is all ARPES studies. And this is a material that's very difficult for ARPES. So what we've done is identified experimental conditions where we can get some good ARPES data. And then from that, in the near nodal region, we identified 3 energy scales where electrons interact with something. And I'll go through the phenomenology of those, how they compare to other cuprates and our interpretations of them. And throughout, I'll be making connections to other cuprates and implications for TC. And in this area, if there are some connections that I missed or some implications that you see that I don't see, I'd be very happy to hear that. So this is the collaboration on this project. So the Mercury 1201 samples come from Martin Greben at the University of Minnesota and his students. Most of the experiments that I'll show have been done at the Stanford Synchrotron Radiation Light Source with user support from Makoto Hashimoto and Donghui Liu. Some other of the data that I'll show have been done at the Advanced Light Source with Eli Rotenberg running that beamline. And on the ARPES side of things, there's my student Sudhir and my former postdoc Antonio. This project was actually began in collaboration with Bob Burgeonow's group back when Ming Yi was his postdoc. She's now an assistant professor at Rice. And Ben Gregory was an undergraduate student that participated. He's now a grad student at Cornell, and my former postdoc, Jay Tanayak, is now a professor at IIT. She also made contributions here, and this work is funded by Air Force. So we have a preprint on this work that covers pretty much everything I'll be talking about today. If there's things that you missed, and I encourage you, if you have feedback on this, please tell me because this is still sort of in the final stages of peer review, so there's still time to make changes. All right, so this is cuprates in a schematic form. So we'll be digging down deeper than this schematic, but I just want to start off here with a very general description. So structurally, the copper or the cuprate high temperature superconductors, they're often depicted schematically as this, where you have copper oxygen planes where all the action happens, where superconductivity happens, where the bands that cross the Fermi energy originate from. So you have the copper oxygen planes, and then you have stuff between them. This stuff is called the charged reservoir layer. And normally people don't talk too much about this stuff. And admittedly, in ARPES experiments, which studied electronic states originating from the copper oxygen planes, we don't access this stuff directly. But it almost certainly is important because of the huge variation in properties among cuprates, particularly the superconducting transition temperature. So another way to think of cuprates schematically is via the phase diagram, temperature versus hole doping, where in the parent compound you have an antiferromagnetic insulator, and then after that is extinguished with hole doping, you have a superconducting dome. So Tc is a function of hole doping with a maximum or optimal Tc at around 16% hole doping. And then the other big character on this phase diagram is the pseudo gap, which is sort of a mysterious normal state, which is bounded by a temperature called T star. So I think there's a lot of agreement on the basics of this phase diagram, although there are a lot of details that people are adding nowadays. But something to keep in mind that I'll come back to in a little bit is that this phase diagram is really constructed from a hodgepodge of different experiments on different materials. So it should be viewed as such, rather than a situation where you can tune one compound over the entire phase diagram, as you can, for example, in iron-based compounds. All right, I'm trying to, oh, there we go. All right, so in cuprates, it's still debated what is the mechanism of high temperature superconductivity after more than 30 years. So I think debated is the diplomatic thing to say, because there are certainly people that have proposed a mechanism or know what the mechanism is, but at the same time, there are also many others that do not agree with those proposals or think that those proposals don't agree with some important data that exist. So the question, like I said, is what is the mechanism of high TC in cuprates? But a different and related and relevant question that I'll be more focusing on today is what is correlated, or what factors occur simultaneously with a higher TC in cuprates. So this is this is probably a different question, but whether this is actually a different question kind of depends on what the mechanism actually is. So if the transition temperature is what it is at formation, then these questions are one and the same. But if there's some initial mechanism of forming superconductivity, and then there are other materials dependent factors that either raise TC or lower TC, then these are kind of two different questions. And given the complexity of cuprates and the huge variation in TC, it's likely the latter situation, where maybe there is some initial mechanism of superconductivity and then other interactions in specific materials that can either raise it or lower it. Alrighty, so I want to spend a little bit of time reminding you or introducing to you, if you're new to this field, some of the ways in which variation in TC plays out in cuprates. So one way that's very well known that I won't get into a lot in my talk is the variation in TC with the number of copper oxygen planes in a block, let's say. So to illustrate that, here are some of my ex-boyfriends, the bismuth-based cuprates. And this is an example of a family of cuprates where one can synthesize materials with one copper oxygen plane in a block, 2 copper oxygen planes in a block, or 3 copper oxygen planes in a block. And as you increase the number of planes from 1 to 2 to 3, the maximum TC in this specific system varies from around 40 to around 100 to 110, I think, in bismuth 223, something like that. So this is an example of one way to raise TC. So change the number of copper oxygen planes in a block. And here's a paper that really compiled a systematic study of this in a number of materials where there exists a family such that one can synthesize compounds that are similar except with different number of copper oxygen planes in a block. And in all or most of these compounds, it's found that TC is maximized at 3 layers per block, and then it goes down. Sometimes it goes down all the way to 0, and sometimes it goes down and then it levels out. And incidentally, this family up at the top, where the black squares, where it has the maximum TC at all number of layers. This is actually the same family as the material that I'll be discussing today, mercury 1201, which is this data point right here. So interestingly, you can see that you can put a lot of copper oxygen planes in a block here. And just in case you have the morbid curiosity to see what a 10-layer cuprate looks like, here you go. Oops, that can pop up. There it is. Yeah, I keep moving my chat and my video screens around. Yeah, so it's kind of a crazy guy. No one has performed ARPES experiments on it, although nowadays with the advent of micro and nano ARPES, perhaps people can. All right. So more relevant to this talk, and perhaps more striking, is the variation in TC among single layer cuprates. And that can be illustrated over here, where I'm showing the most common cast of characters in this category. So there's mercury 1201, which I'll be discussing today, that has a maximum TC of 98 Kelvin. And this is contrasted to LSCO, which is perhaps the most commonly studied single layer cuprate, taking into account all experimental techniques. And this guy has a TC max of only 39 Kelvin. There's another single layer cuprate, thallium-221, that has a maximum TC of 95 Kelvin. It's also very seldom explored in general. There are relatively few studies on it as compared to other materials on this slide. There's bismuth 2201, which I showed on the previous slide, and then there is sodium doped CCOC. So throughout this talk, when relevant, I'll be making comparisons to LSCO, bismuth 2201, and sodium doped CCOC, which are structurally similar to mercury 1201 in that they have one copper oxygen plane per unit cell, but they have much lower TC. So just a small note. At first glance, it might look that like the structure of mercury 1201 is very different from the other single layer cuprates. It is a little bit simpler, but basically as a point of reference, in mercury 1201, this unit cell is what it is. There's one copper oxygen plane in the unit cell. For most other single layer cuprates, there are actually technically two copper oxygen planes inside the unit cell. So there's the one over here, and then the next one is actually offset by half a unit cell in the plane. So you can see here the oxygen is in, or rather the copper is in the middle. Here the copper is at the corner. So the bottom block is essentially the same as the top block, except offset by half a unit cell. So good. There's a question. Do you have any comments on what causes the TC max variation among these families? Yeah, I do actually on the next slide. So I'll come to that. And there's actually a lot of proposals that I'll probably not cover all of them, but let me go ahead and get there. Good, and there's another question. Why is LSCO the most studied if mercury 1201 is simpler? Mercury 1201 is simpler structurally. It is more difficult to make large single crystals. So LSCO, I mean, it's, I'm not going to say it's ever easy to grow a large single crystal, but for LSCO, you can get single crystals that are larger than my finger. And then for mercury 1201, single crystals still to this day are maybe 2 millimeters max. Additionally, for surface spectroscopies, LSCO, it's a little bit difficult, but it's not as difficult as mercury 121. So the answer to that question is that mercury 121 is just more difficult to grow and to study. All right, so let me move on to the next slide where I'm going to address the question about the causes of this TC max variation. So, all right. So there are a lot of different proposals for the variation in TC and among single layer cuprates. And I just want to highlight a couple of them. This is not meant to be an exhaustive list, so I apologize if your paper has been left out. But proposals include disorder, which is discussed in this Asaki paper. And then there are a number of proposals right here, which are all kind of interrelated to one another. So there's an observation that the apical oxygen height, so the height sort of in this octahedron, the height of this oxygen right here, that's not explicitly drawn there. So this varies among single layer cuprates, and the ones that have the higher TC tend to have the larger apical oxygen height. So with this variation in apical oxygen height, there are sort of aspects of the electronic structure that vary because of different hybridizations of the copper DZ orbital into the electronic structure. So for example, the shape of the Fermi surface is something that varies. The lower TC materials tend to have a more diamond-shaped Fermi surface, whereas the higher TC ones have more cylindrical barrel-shaped Fermi surfaces. And then aspects of the higher energy band structure also can vary with the apical oxygen height, which includes the charge transfer gap, but also various other bands as discussed in this paper on the right. And another suggestion that's been made is the polarizability of the charge reservoir layer, which is the physical component that varies among different among different single layer cuprates. So I would say it's still an open question why there is this variation. But the information that I'll be focusing on in these slides that does not exist presently in the literature is excitations with energy scales relevant or to TC, so energy scales that are comparable to the superconducting gap. So things ranging from, let's say, 10 to 200 MeV rather than 1 eV. So this is something that can be characterized by ARPES and specifically sensitive to excitations that electrons care about. And this is something that's been characterized in some of the lower TC single layer cuprates, but not really in the higher TC ones. So good. So there's another question. How does the shape of the Fermi surface relate to TC? So that's perhaps a question that's a little bit outside my wheelhouse, but generally you can change so one way to think about it is you can change the shape of the Fermi surface by changing the relative intensity of the first nearest neighbor hopping relative to the second nearest neighbor hopping. And this sort of property of the interaction, so how long range they are, do they promote or prohibit hopping, is something that can have direct relevance to TC or to the mechanism of superconductivity. Good. So let's move on. Another aspect of materials dependence is something that all experimentalists know, is that certain materials are just better suited for certain experimental techniques. And in this slide, I want to highlight that variation that exists, and also illustrate that most cuprates cannot be doped over the entire phase diagram. So as a warning, this is not intended to be an exhaustive list. So I'm not claiming that neutron scattering is the only experiment that's performed on LSCO, not at all. And obviously, I'm also only looking at the whole dope side. So, so basically, there are very few materials that can be doped over the entire phase diagram. So from the parent compound to beyond the superconducting dome. And the ones that do have this property also happen to be the ones that have lower TC. So this is something that is kind of hard to solve. That's a chemistry problem, and we can't, you know, that it might be an insurmountable problem, but it is something that we should be aware of when thinking about this phase diagram in its totality. So something that we can do something about is this sort of siloing of different experimental techniques for different materials. So for example, among the bismuth-based cuprates, these are very good for surface spectroscopy, such as ARPES and STM. But they're very difficult for things like X-ray and neutron scattering and transport experiments. And oppositely, YBCO is a material that can be grown very clean, and it's great for transport and scattering experiments, but very difficult for ARPES. So the last material down here, mercury 1201, is one that is sort of in a similar category for YBCO. So there is a wealth of transport and scattering data, but very little information from ARPES. And I think this is an important issue to address because when you observe a phenomenon in a material, you really want to be sure that this is sort of not a technique dependent phenomenon. So something that a given experimental technique is really sensitive to, and that a given material exhibits strongly than other cuprates. So this is all I'm going to say on the topic of materials dependence in an introductory manner for now, but I'll come back to it throughout the talk in reference to some of our data. But as I mentioned, I think this is a really important area to pursue in this sort of mature state of the cuprates field right now, when we have a lot of information from the usual cast of characters, which is the ones on this slide, and we have some really mature experimental technology which can target difficult materials. And we have, you know, hundreds of cuprates that have been discovered a long time ago, but never really studied with modern experimental techniques. So with that, I'm going to move into a different type of introductory information on angle resolved photoemission spectroscopy, just in case you're new to this. And there's also another question that there's a question for thallium-2201. It seems like the accessible doping range is quite high. Does one reach the underdoped side at all? As far as I'm aware, no. So it can pretty much be only grown overdoped and up to optimal doping, but not really on the underdoped side. So that is sort of unfortunate in some sense, but on the other side of the coin, it's kind of the only cuprate that is really optimized in the overdoped regime. And that is a unique attribute that I think has not been exploited enough, because there's sort of an assumption yeah, I would say it's an assumption that everything on the overdoped side is just very conventional, very boring. But at the same time, you know, in overdoped thallium-2201, you might have a TC of I don't know, 50 Kelvin, 60 Kelvin, which, you know, is still relatively high. So I think there's a lot we don't know on the overdope side, and that's another example of opportunities that exist from studying lesser studied cuprates. Good. Are there other questions about the previous slides before I start over here? Okay, good. And I really appreciate the questions that have come in the chat. Alrighty, so angle resolved photon emission spectroscopy, it is a fairly ubiquitous technique nowadays, and it is based on the photoelectric effect. So UV light shines on the sample, photoelectrons are emitted, and then the analyzer measures their kinetic energy and emission angle, which is related to very simple formulas to the crystal momentum and binding energy that they had back when they were inside the solid. So a typical spectrum might look like this, binding energy versus crystal momentum. And nowadays, one can get a spectrum like this in maybe a minute or less, unless you're studying cuprates, and especially mercury 1201, which have a very low density of states in the valence bands, where it does take longer. But in any case, in this image plot, the intensity at every value of K and omega is can be related to this formula, which has a number of terms, most of which we won't really use today. But one term that's implicitly going to be beneath the surface is this first term, which is called a matrix elements term. And it basically describes how experimental conditions, such as your experimental geometry, the photon energy, the polarization, will affect the intensity of the spectrum that you see. There's a Fermi-Dirac cutoff, so we only see occupied sides. And then finally, the meat of the experiment is this K of omega term, the single particle spectral function, which contains information both about band structure and interactions simultaneously. And I'll come back to this later on as well. So there are two ways to slice up ARPES data. So the one way is the energy distribution curve, or EDC. And the EDC is found by sticking to one momentum and looking at the intensity as a function of energy. And this type of analysis can be useful for learning about spectral gaps, line shapes, things like that. Then there's the orthogonal way of slicing the data, the momentum distribution curve, or MDC method, where you stick at a constant energy and you look at the intensity as a function of momentum. And this is the usual way of tracking band dispersion. So basically, at every energy, there's this usually Lorentzian peak, and its position marks the band position at that energy. So there's a question, is EDC density of states? It is related to density of states. If you, so there's a couple of subtleties. One is obviously it's a momentum resolved quantity. So you'd have to average over all momenta to get something comparable to what, for example, STM sees. The other caveat is that there is the matrix, so there is the photo emission process that can sometimes make it not exactly be the density of states. So if you have poor resolution, it can broaden it out. If you have a three-dimensional sample, it can also broaden it out. So it's related to density of states, not exactly the same thing. Other questions? All right. Let's move on. So ARPES has really been an invaluable tool for learning about cuprates. And I would put the contributions to our understanding of cuprates into two broad categories. So the first broad category is measurements of gaps. So the superconducting gap and the pseudo gap, which is also a gap. And this can answer questions like what is the pairing symmetry and what state does superconductivity emerge from? So the superconducting gap in cuprates has what's called a D waveform, and in for the specific fermiology of cuprates, what it means is that there's one momentum on the Fermi surface, and this is 1/4 of a cuprate Fermi surface. It's a whole like Fermi surface centered around pi pi, or the zone corner. So there's one momentum where the superconducting gap is identically 0. That means that it's not just accidentally 0. So the phase is, for example, negative over here and positive over here. So it has to go through 0 to get there. But in ARPES, we only measure the magnitude, not the phase. So there's the node where the superconducting gap is identically 0. And then there's the antinode where it is maximum. And the antinode is located on the Brillouin zone boundary. So this terminology, node and antinode, it originated from the D-wave superconducting gap, but in the cuprates field, even in the absence of superconductivity, we use this language to refer to these regions of the Fermi surface or these regions of the Brillouin zone. So the node is basically where the Fermi surface intersects the zone diagonal, going from 0, 0 to pi pi. And this is where we're primarily going to be for this talk. The antinode is along the zone boundary, and it's used sort of synonymously as the zone boundary. So that's one aspect of ARPES studies on cuprates, most very broadly speaking. And this is not where we're going to be today. So instead, today, what I'm going to be discussing is dispersion anomalies. And what dispersion anomalies tell us is what excitations electrons couple to. So they tell us this information indirectly. And perhaps some of these excitations might be related to superconducting pairing. So a dispersion anomaly is basically anywhere where there's a deviation from a monotonic dispersion. And I'll quantify that a little bit more later on. But this area is where we're going to be today. We're going to be talking about dispersion anomalies in mercury 1201. And I want to emphasize that even though ARPES has made really tremendous contributions to our understanding of cuprates, this understanding has come from a small number of compounds that exist. I would say that over 90% of the ARPES studies in the literature are on maybe 3 cuprate compounds. So there's really a lot of open space there, despite the maturity of the field and the technique. All right. Okay. So this brings us to mercury 1201, which in my title I claimed is a model single layer cuprate, and it is called a model single layer cuprate because, as was alluded to by one of the questions, it is structurally very simple. It has only one copper oxygen plane per unit cell, and moreover, it is tetragonal. So many other cuprates, although they're nominally tetragonal, they're small. There are small sort of modifications that happen in real materials that actually make them a little bit orthorhombic. So this is actually an important distinction, not for my talk, but in the context of modern research, where there are many proposals involving the breaking of fourfold symmetry, in which when you already break that symmetry structurally, it's harder to make the argument that that it's a spontaneous breaking of electronic symmetry that just happens without any nudge. So, so they're a model material in that they are tetragonal, single layer, and additionally the dopants, which are oxygen, sit in the mercury layer primarily, which is very far from the copper oxygen planes. And just as a side note for those that don't know, to change the doping in mercury 1201 and also a lot of other cuprates, you need to change the amount of oxygen. So this is done by either annealing in an oxygen rich or an oxygen deficient environment. So this model nature of mercury 1201 is realized by the wealth of studies that exist from techniques other than ARPES. So it's very well studied and characterized by transport. And there are also extensive neutron and X-ray studies. So the latter is what I'm going to focus on in this talk, but the former is important. And of course, I'm leaving out many other experimental techniques that have yielded beautiful results on this material, optics, and microwave experiments. This is just a space-related omission, but it's been very fruitful for other experiments, but unfortunately, it's very difficult for ARPES. So the difficulty for ARPES is twofold. So first of all, there's no neutral cleavage plane, and as I'll show in a little bit, that is actually probably okay. The second difficulty is that it is very sensitive to experimental conditions. And this is kind of the more difficult stumbling block that has caused there to be so little ARPES study of this material in the literature. So regarding the lack of neutral cleavage plane, what that means is that there's nowhere to slice the crystal structure and get the same thing on both sides if you're slicing strictly parallel to the copper oxygen planes. So in other single layer cuprates, I mentioned earlier that they have the actual unit cell is actually kind of double this one, where the second copper oxygen plane is offset by half a unit cell. And it turns out in those structures, you do end up getting kind of a situation where you have the same thing on, there's a plane where there's the same atoms on one side of the plane and the other side of the plane. So that sort of gives you hope for a neutral cleavage plane. In mercury 1201, this does not exist. So because there's not an obvious place to slice the mercury 1201 crystal structure, this begs the question, where does mercury 1201 cleave? And this is actually something that we can answer with photoemission techniques, and not angle resolved photoemission spectroscopy, but with angle resolved XPS, so looking at core levels in an angle resolved manner. So so angle resolved photoemission spectroscopy is well known to be a surface sensitive technique whereby whereby 70% of the signal originates from this depth indicated by the electron mean free path, which at the photon energies that we're talking about is maybe something like 10 angstrom or so. So let's consider a photoelectron that originates from a distance lambda below the surface. And first we consider a scenario where this photoelectron is coming out normal. So it needs to travel distance lambda to exit the surface. Now let's rotate the sample and consider an electron that or a photoelectron rather, that again needs to travel a distance lambda to exit the surface. So now it's not going to be traveling orthogonal to the surface, it's going to be traveling at some angle. So for it to travel a distance lambda, it actually needs to originate from a depth lambda cosine beta. So essentially by varying the angle, when you get to larger angle, you are sampling a region that is closer to the surface. So then by looking at core levels, which originate from different atomic species, you can sort of try to figure out which ones are close to the surface. So here we've looked at a portion of the core level spectrum, looking at 2 mercury and 2 barium core levels. So for the barium core levels, they systematically and monotonically get weaker as one moves to higher and higher angle, whereas the mercury ones do not have this behavior. So this suggests that mercury is closer to the surface when we cleave. So the cleave happens closer to the mercury layer and further away from the barium layer. So going back now in the next slide to the crystal structure, it turns out that this is actually kind of good news. So if we look at the crystal structure, so here's the mercury layer, and here is the barium layer above it. And we just learned that cleavage happens closer to the mercury layer. So, to break near the mercury layer, you can see that there are these symmetric bonds, oxygen, mercury, oxygen. So the bond is symmetric above and below the mercury atom. So if we're cleaving near the mercury plane, what's most likely happening is that we have sort of the bonds being broken alternately above and below the mercury. There's no reason to expect them to be preferentially broken above or below because they are symmetric, like I said. So looking at the charges of the different layers, the oxygen and the mercury have equal and opposite charge. So if you have equal amounts of mercury and oxygen on the cleaved surface, this is technically a charge neutral surface. And this is borne out with our earlier study looking at the Fermi surface and comparing it to the doping. So this was a compound that had a nominal doping of 14%, and the area of the Fermi surface that fit the Fermi crossings best was found to be 11 to 13%, and in the area of the cuprates, this is very good agreement as far as Fermi surface area. So it looks like the cleavage surface is probably charge neutral, and the doping that we measure in ARPES is reflecting the nominal bulk doping. So that is good news. There is bad news, however. The bad news is that there is a huge amount of sensitivity to ARPES experimental conditions that I previously alluded to. And it is for this reason that it was only in 2014 that there was actually a peer-reviewed ARPES paper on this material. So in that work, we found that 19.4 eV photon energy really optimized the spectrum. So these are EDCs looking at the nodal point at KF, and as the photon energy is cranked up from 18.6 to 19.4, this EDC peak gets largest, and then it starts to decrease at higher photon energy. This can also be seen by looking at the image plots themselves. And I should say that that these data that I'm showing are for a really bad cleave. So the spectral quality is not great, but it still gets the point across. And the point is that at the optimal photon energy, we see a band dispersing all the way towards EF. Then when we move away from this optimal photon energy, we see a band dispersing, and it becomes faint as we approach EF, but we can still track it going there. And then when we move to even higher photon energy, we lose the band and we just see a blob. One can argue that the blob has some physical origin, but I'm not so sure. So anyway, this is an example of the sensitivity to ARPES experimental conditions. So in this talk, I'll be discussing exclusively data taken at 19.4 eV photon energy close to the node. So I should caution that this is not like the one and only magical photon energy that works. We found other conditions more recently that also yield good data. But it's just in a less mature state, such that I can't really comment on it at this time. So for this talk, we'll be doing 19.4 eV photon energy and sticking close to the node. So there's a question: what are the possible reasons for the strong dependence on photon energy? Okay, very good question. So in general, for all materials that you might do ARPES on, there is a strong photon energy dependence. So for some material, so one aspect of this is the generic material is three-dimensional, and you access different slices in the 3D Brillouin zone with different photon energies. This is not really relevant to mercury 1201, which is very two-dimensional. Beyond that, there's what I mentioned earlier, the intensity of the photoemission signal. It has a prefactor, which is this matrix element term, which originates from dipole transitions from the initial state to the final state in the first step of the photoemission process. So it's a term that really depends on experimental conditions, photon energy polarization, things like that. So it's a general fact that even in two-dimensional systems, some photon energies will just give you brighter spectra, even they'll just give you brighter spectra because of the matrix elements term. And this is what I think is happening here. The confounding factor in Mercury 1201 is that the spectral intensity of the valence bands in photoemission, it seems to be smaller than in other cuprates. This could be just because the cleaved surface is not ideal, but the intensity is smaller to begin with. So when you take a natural, a typical variation in sort of the photoemission cross section, and then multiply it by a factor that continuously makes it even worse, you'll get some photon energies that give you something, and other photon energies that give you nothing. So it's a confluence of factors, in other words. Are there other questions here? All right, and thank you to you guys who are asking questions. These are really good ones that are coming out. All right, so in any case, we have found experimental conditions that yield good ARPES data in Mercury 1201. And if we are lucky enough to also get a good cleave, then we can get a beautiful spectra like this. And an incoherent background has been subtracted far away from the band, which makes it look a little bit even more prettier than from previous slides. So this is a spectrum at optimal doping, and this is an MDC dispersion for that same spectrum. And I want to walk you through the three energy scales that we see. So first, we have the low energy kink, which in this material is around 11 MeV. Secondly, we have the intermediate energy kink, which used to be the low energy kink before the low energy kink was discovered. So the intermediate energy kink is a feature that is ubiquitous in cuprates. So it'll be an opportunity to make comparisons among other single layer materials. And finally, in the MDC dispersion, you can see that there's another slight bend at around 200 MeV. If you don't see it or you don't believe me, that's okay, because this feature, we study it instead in the EDC channel, where the key observation is this peak dip hump line shape. And notably, this is a peak dip hump line shape at the node. All right, so going back to our motivation. So what we observe is that there is a deviation from a monotonic dispersion. So there are these places where the dispersion bends suddenly here, here, and here. And if you don't believe that, you know, if you believe that this is just a gradual band evolution, the point of comparison is sketched out over here with the dashed blue line. So this is approximating a tight binding band for this material. And although locally, when you look at the dispersion, it does seem to be continuous, at least maybe for some of the features I've pointed out. It should be noted that the band bottom for a nodal cut is like down at -1 eV. So on those energy scales, these changes are definitely discontinuities and not just natural band curvature. So anyway, the deviations from a monotonic dispersion, they indicate coupling between electrons and some other degrees of freedom. So broadly speaking, and these types of dispersion anomalies are observed not just in cuprates. Broadly speaking, they can be attributed to phonons, magnetic excitations, correlations, other things. And then the significance of these features in the ARPES spectrum is that they reflect interactions between electrons and something. So other techniques might measure excitations, but ARPES says, okay, this is the energy scales where the electrons are actually caring about something. So these interactions could be ones, if we can figure out what causes these dispersion anomalies, these same interactions might affect TC, or they might affect competing phases. All right, so our approach is the following. From the ARPES side of things, the knobs that we have available to us are temperature dependence, doping dependence, and momentum dependence. So we can characterize the dispersion anomalies as a function of all of those properties. Then the advantage of mercury 1201 is that these materials are already very well characterized by other experimental techniques. So we can see what collective excitations have comparable energy scale and behavior. And then we can also make comparisons to other cuprates to address the question of, are these universal or materials dependent behavior? And also, do they have any correlation with TC? So I'll be making comparisons along two axes. So one is going to be comparing to other single layer cuprates, and the other axis is going to be comparing to multi-layer cuprates that have comparable TC to mercury 1201, namely bismuth 212. So with that, okay, we finally get into the data in more detail. So what I'll be showing for the next little bit are MDC dispersions. So at every energy slice, we fit a Lorentzian and get the peak to track the dispersion as the function of energy. And everything that I'll be talking about, unless stated otherwise, is going to be a nodal cut because that's where we have the largest cross section. So the first feature that I'm going to discuss is the one that's being pointed to by this pink arrow over here. So that pink arrow arises because if you consider the real Fermi velocity right at the Fermi energy, so the slope of the dispersion, and you follow that slope, you see that at slightly higher energies, the measured dispersion starts to deviate from this initial slope. And the energy where this occurs is around 11 millielectron volts. The renormalization across this kink, we call it, so the ratio of the velocity above this kink to the velocity below is approximately 2 for all of the dopings that we looked at. So this is a feature that is not strictly new, but it is new outside the bismuth-based cuprates. So, oops. So this feature is called the low energy kink. And the low energy kink, it has been discussed in the context of bismuth-based cuprates, so bismuth 2212 and bismuth 2201, but like I mentioned, not any other material. So this is the first report of the nodal low energy kink in a cuprate other than bismuth 2212 or 2201. So in bismuth 2212 and 2201, it was discovered about a decade ago when high resolution laser ARPES came into existence and allowed to resolve dispersion anomalies very close to Fermi energy. Importantly, the low energy kink occurs at sub-gap energies. So sub-gap meaning smaller than the maximum of the superconducting gap, which is around 40 millielectron volts in mercury 1201. So what that implies is that the excitation only sees the local superconducting gap, local in K space, not the superconducting gap in the rest of the Brillouin zone, where it is larger than the kink. And I'll come back to why this I'll discuss sort of this in a little more detail later on. But the explanation for the low energy kink has been in terms of coupling to phonons, so either acoustic or optical. So this work by Steve Johnston in 2012 that I was a part of argued that it was due to coupling to acoustic phonons, but later on when the acoustic phonon dispersion of bismuth 2212 was actually measured, it was found that quantitatively this probably isn't going to work. There's no way to satisfy both the energy and the momentum constraints. So now it seems more likely that it's due to optical modes. So this is a feature that a lot of people actually don't know about, but it's significant in the sense that if you want to interpret quantities involving the ground state effective mass, you need to know the real Fermi velocity right at the Fermi energy, which given the low energy kink is a little bit smaller than the Fermi velocity at higher energy. So this is an important quantity in terms of connecting to other experimental techniques. It appears that the low energy kink originates from modes coming from charged reservoir layer atoms. So it's been argued in some of the papers that I cited on the previous slide that a phonon to be coupled only at small q or an acoustic or rather an optical phonon, rather, it needs to have A1G symmetry. And some of the candidates in the bismuth-based cuprates that have the correct energy are shown here. And for the most part, they involve motions of heavier atoms. So in the case of the bismuth-based cuprates, the strontium atoms, which are here, and the bismuth atoms. So atoms in the charge reservoir layer. In mercury 1201, when we look at the energies that we see, and if we're generous with the energy range of the low energy kink, one would say that it's between 8 and 15 MeV in our experiments, but generally around 11 MeV. And from the phonon density of states, it looks like this is smack dab where the barium derived modes are. So again, involvement of the charge reservoir layer. So this low energy kink, I think, is an important window into the charge reservoir layer, but the renormalization at optimal doping is similar in mercury 1201 and bismuth 2201, which suggests that it's probably not related to the difference in TC. So I'm about to move on to the intermediate energy kink. Are there any questions about this feature before I do that? All right, so let's go ahead and move on then. Now we move on to the intermediate energy kink, which is this blue arrow. It occurs around 55 MeV in mercury 1201. And this is a feature that is ubiquitous in all cuprates. And I have a small selection of references that discuss it in terms of experiment and theory. But I apologize if your paper has been left out, because this is only a small selection, I realize. So the intermediate energy kink, it is ubiquitous in all cuprates, and it has been attributed to a number of things, including phonons, magnetic excitations, a gapped continuum of excitations, and electronic correlations. And there's a question from Louis. Can you relate your measured Fermi velocity to other measurements of the mass, like the effective mass in quantum oscillations? Yeah, so that's a good question. We haven't done this here, but as you know, you need to make an assumption about what the Fermi surface is. So you need to sort of make the assertion we're looking at a small pocket or a large pocket. Presumably, one would compare to a small pocket in this case. We haven't done that quantitatively, but that's a good idea. All right, so going back over here to the intermediate energy kink. So I would say nowadays the explanations have sort of converged more on looking for a sharp bosonic mode, phonons or magnetic excitations that could cause it. But given that it's sometimes a more gradual change in the Fermi velocity, it is possible that there are other contributions. So with that, I want to go through the phenomenology that we see in the ARPES experiments on Mercury 1201. But before I do that, just a little bit more background. So as I mentioned, the meat of the ARPES experiment is the single particle spectral function, which has information about band structure and interactions. And there are two parts of the self-energy which encapsulate these interactions. There's the real part of the self-energy, which tells you how interactions affect the band position. And there's the imaginary part, which tells you how they affect the line width or the lifetime. So in regards to the real part of the self-energy, so in ARPES experiments, we have the measured dispersion, which is shown here in red, and then we have an assumed bare band. So in this expression for the single particle spectral function, the bare band is this E sub k. So a priori, we do not know what the bare band is because we measure the whole shebang, the bare band and the interactions on top. So one usually makes some assumption of what the bare band is. So common assumptions include a tight binding bare band, an LDA bare band, something like that. In the slides that I'll show, we used the assumption of a tight binding bare band, but there's the caveat that since we don't know what the actual bare band is, what we're actually reporting is an approximate real part of the self-energy. So this approximation is okay if you use the same criterion throughout the analysis, and that's what we do, and that's kind of the customary way of doing this. So after the measured, the assumed bare band is subtracted from the measured dispersion, you get something like this, which approximates the real part of the self-energy, and the energy position of this very broad peak gives an estimate of the kink energy. So it should also be noted that the imaginary part of the self-energy is Kramers Kronig related to the real part. So all of the information that we get from the dispersion should also be available from the MDC width. And indeed, we do see something happening at a similar energy in the MDC width, although it is fairly well known that especially when the spectra are less than ideal, as is the case with Mercury 1201, it is much harder to extract these features from the line width than the dispersion. So basically, we can track the band position much more precisely than we can track the intrinsic width. So that the energy dependent of line width is just a double check that we actually, are seeing a genuine feature. So there's a question. How can we relate the deviation from the assumed bare band to spin or charge fluctuation? How can we distinguish between spin and charge contributions? So, so basically, the idea is that the excitations, the potential explanatory excitations, the things that electrons might be strongly coupled to produce the kink, they have some temperature dependence, some doping dependence, some Q dependence, and then we correlate this to what is seen in ARPES to make the best hypothesis about what causes the kink. So it's sort of a technique. It's a phenomenological argument that incorporates multiple techniques to make its assertion. And I'll kind of walk you guys through how we do this. All right, so the first knob that we have available to us in ARPES is doping dependence. And And here I'm showing the 3 different dopings that we looked at. Lower doping at the top, optimal doping at the bottom. Oh, sorry, I missed, I didn't write down the temperature. So on this slide, everything is well below TC. Everything is at 30 Kelvin. Here, the feature does become broader as we go into the more underdoped regime. But if we do want to define a doping dependence, one would say that the energy gets slightly lower at higher doping. And Piers, I'll come to your question in just a moment. So anyway, so regarding doping dependence, we see a weak doping dependence or a slight softening of the kink energy. This is something that's a little bit more difficult to quantify. So if you don't believe that there's any doping dependence, I won't necessarily be offended. So Piers, going back to your question, about the gigantic imaginary part of the self-energy. So I should say again that this is also an estimate. So the way that this is actually derived is from the MDC width, which is in units of momentum, and then it's multiplied by a Fermi velocity, in this case the bare band Fermi velocity, to get it into units of energy. So one reason that it is so large is that in Mercury 1201, there are factors that artificially broaden the line width, probably deviations from an ideal cleaved surface. So the line width is, for example, several times larger than in bismuth 2212. So sometimes people sort of subtract out this value at 0 energy which is probably what we should have done here, but we don't really use this style of analysis, rather other than in a qualitative way to say something happens at a similar energy. Right. So we have a weak doping dependence, and if you don't believe that there's a doping dependence, then I'm not offended. Then with temperature dependence, we have a minimal temperature dependence. So what we're looking at is kind of the intensity at the maximum, and we have kind of a large temperature range here, going from 30 Kelvin, which is well below TC, or 50 Kelvin in the case of the optimally doped case, to about 160 Kelvin or 150 Kelvin, which is well above TC. And in that temperature range, we see a relatively minimal temperature dependence of the intensity of the maximum of the approximate part of the real part of the self-energy. So I should mention that the pseudogap temperature T star in these materials is kind of high, and we can't really access it in our experiments, not because we can't turn up the thermometer that high, but because if we go too hot, then oxygen will leave the surface and change our doping. So we only analyze our data in the regime where we still have good data. So we have a minimal temperature dependence, and if you don't believe that it's minimal, let me compare this to bismuth 2212, where in the same temperature range, the intensity of the maximum decreases by about 50%, whereas at most in a Mercury 1201, it decreases by 25%. So the temperature dependence is minimal as compared to bismuth 2212. So the last piece of information we have is the momentum dependence. And this is where we have data away from the node. And again, this is still at low temperature, still at 30 Kelvin. So what we see in terms of momentum dependence is that the kink weakens strongly moving away from the node, such that when one is sufficiently away from the node, it is consistent with 0. So So this is something that is quite striking in the Mercury 1201 data, the strong weakening of the ubiquitous intermediate energy kink away from the node. And now we get into interpreting these data. So just a small note on the note on interpreting. So one, all of this discussion is already assuming that the kink originates from coupling to a sharp bosonic mode. And this assumption is kind of justified, I think, because if you look at the MDC dispersion, and this is the best one we have at optimal doping, you can see that it has a slight S shape. Okay, over here, it kind of curves in before it comes back out. And this slight S shape is kind of a signature of coupling to a sharp mode as opposed to some broad continuum. So in this context, there are kind of two interpretations, or rather two places to look for bosons. So one is if the electron boson coupling is isotropic, so a fermion at the node can be scattered to the antinode using the boson in question, then the kink energy in most scenarios will be gap shifted by the superconducting gap, which we previously measured to be around 40 millielectron volts. So in this scenario, we would look for modes at 10 to 20 millielectron volts. The other scenario is the electron boson coupling is either peaked at small q, or it is peaked at or it is has a momentum dependence, for example, where it connects only node to node, so only small gap to small gap. And here the kink energy would reflect the mode energy, and we would look for modes at around 55 MeV. So given the weak temperature dependence, and specifically given that we don't see a gap shift of the maximum position across TC, it really suggests that we are in the second scenario, that we need to be looking at excitations that are actually at 55 MeV. And fortunately, in Mercury 1201, these are well characterized. So from neutron scattering, there are these icing-like excitations that exist throughout the Q space, and have the correct energy at optimal doping. There are the antiferromagnetic fluctuations, sometimes called magnetic resonance mode, but in Mercury 1201, there's actually not an hourglass-shaped dispersion. There is a Y-shaped dispersion, and the maximum intensity is also at the correct energy scale. And also from inelastic X-ray scattering, there's information about what the phonons are doing. And there is this breathing mode branch that softens approaching a larger Q. And this softened energy matches very well with our kink energy. And also, if we're considering gap shifted possibilities, there are some phonons around 20 MeV that might do the trick. But as I mentioned, because of the weak temperature dependence across TC regarding the energy position of the maximum, we are probably not in a gap shifting scenario here. So getting into the discussion now. So the doping dependence, as I mentioned, there is a slight softening. And I also mentioned I'm not offended if you don't believe me. So the icing-like excitation that matches the energy that we're looking at does not appear to have a doping dependence, whereas the excitation near the antiferromagnetic Q does have a doping dependence, and this doping dependence is actually opposite to what we see. So in these data, the symbol is the higher doping, and the axis is also flipped from mine. So the peak in the susceptibility is at slightly higher energy for the higher doping. So it actually has the opposite doping dependence of what we see. So then but instead, if we consider in-plane oxygen modes, specifically a large momentum transfer, they do appear to have the correct they do appear to have the consistent doping dependence. And specifically, there are two breathing modes. There's with different displacement patterns, a longitudinal breathing mode and a longitudinal half breathing mode. And they both have some softening with doping, and the half breathing mode is the one that for this material and other cuprates as well appears to also have the correct energy. So moving on now to the temperature dependence. So the temperature dependence is where we really find inconsistency with the magnetic mode at the antiferromagnetic Q vector. So specifically, a recent finding in this field has been that this resonance mode, which was previously thought to be associated with TC, it actually persists to higher temperatures, and if one were to assign a temperature scale to it, it would actually be T star. So it seems to be more sensitive to T star. As a corollary of that, if this mode were causing this kink, one would expect a strong temperature dependence of the intensity of the maximum, which we do not see. And these circles here highlight the two temperatures we're comparing, well below TC and at around 150 Kelvin. So that aspect is more consistent with a lattice scenario where there is not this strong temperature dependence as there is with the magnetic excitation. So finally, there is the momentum dependence, which really is the most consistent with this half breathing mode. So one way to think of this is a simple hand-wavy kinematic argument where at the node, the Q connecting one node to the opposite node, but not at the Fermi energy at minus 55 MeV, matches well with the Q where inelastic X-ray scattering observes the same energy, whereas at smaller whereas once you get into this regime close to Q equals 0, you can no longer traverse these two constant energy contours. And this is an argument that's been made prior in the literature, for instance, in bismuth 2201. However, experimentally, the situation in mercury 1201 is a little bit simpler because in mercury 1201, they observe sort of a shift in the kink energy at some specific momentum, whereas in mercury 1201, we actually observe the kink going away at a certain momentum, which is consistent with prior calculations, which showed that the breathing mode, the coupling to the breathing mode is actually strongest at the node. So finally, I want to make comparisons to other single layer cuprates. And what I'm showing here is from the literature, MDC dispersions at the node as close to optimal doping as I can find, comparing sodium dope CCOC, LSCO, bismuth 2201, and mercury 1201. The arrows in all of these come from these data right here, which measure the phonon dispersions, and specifically for this half breathing branch, which softens approaching the half zero position. And here I'm circling the relevant energy scales, which seem to match very well with what's in the data. And specifically, the kink energy in LSCO is somewhat larger, tracking the materials dependence of this specific mode. So another thing to point out is we can also quantify the velocity renormalization across this kink, which doesn't exactly tell you the coupling strength, but it's related to it. And we see that the velocity renormalization in mercury 1201 is significantly larger than for the other single layer cuprates. So the identity of what causes this kink is somewhat separate from the relationship between that excitation and superconductivity. And the half breathing mode, it has been interpreted in various ways in relationship to superconductivity. So there are papers saying that it's bad for D-wave superconductivity. It might be the case, but the fact that there's such strong coupling to this mode in mercury 1201 and high TC suggests that this is probably not the case. There are also suggestions that it may be good for superconductivity, not that it necessarily causes superconductivity, but that it may be a mechanism for enhancing superconductivity. In the present data, there is sort of indirect support for this given the large renormalization and the large TC. There are also proposals that is unrelated to superconductivity. For example, the fact that it is present at non-superconducting dopings. We can't rule out the idea that it is unrelated to superconductivity, but we have, I would say, strong evidence that it's not bad for superconductivity. So finally, on the intermediate energy kink, I want to highlight some materials dependence, just in case you're looking at these data and you're thinking, this is not what I remember. So in bismuth 212, the behavior of the nodal kink is actually different, which can also be consistent with a lattice description. So specifically in bismuth 2212, there's strong temperature dependence, no doping dependence, and the momentum dependence is opposite. The kink gets stronger approaching the antinode. In these data, the kink energy is over here. The stuff closer to EF is related to the superconducting gap and not part of this discussion. So this can be, this is consistent with considering anisotropic coupling to two different phonons. So a buckling or B1G phonon for the case of 2212 and other multi-layer cuprates. The argument there is that the B1G mode does not couple to electrons in single layer cuprates to first order. So the first two statements are I'll let it stand. But interestingly, the B1G mode has been associated with enhancement to superconductivity, not to the primary mechanism of superconductivity necessarily, but as a factor that can enhance TC if it is onset separately by some other factors. But however, in single layer cuprates, there is no coupling to first order to this mode. So where does the enhanced TC in mercury 1201 come from? And that is an open question. So finally, I want to get into the last energy scale, which I'll go through quicker, and that is the nodal peak dip hump structure. So this is something that exists in the literature already, but it has not been really discussed in modern times. And I want to draw your attention to it again, because with the inclusion of mercury 1201 data, we do have some implications for the phase diagram. So the features that I'm talking about, and on the left side, I have mercury 1201, and red EDC is at KF. These are, again, nodal cuts, low temperature, 30 Kelvin. There is this peak dip hump structure at the nodal KF, and also KF a little bit, or rather not KF, momenta a little bit away from KF. This is in contrast to bismuth 2212. Oh, Juven is telling me to slow down. Okay, yeah, I guess people can catch this on YouTube if they gotta go. All right, so in bismuth 2212, this is also, this is around optimal doping. We see a very different behavior at the node, where at higher energy or momenta away from KF, you do have these broadly peaked features, broadly peaked line shapes. But as you move closer to KF, they sort of just smoothly evolve into these sharp peaks corresponding to the coherent part of the dispersion. So there's nowhere where there's this breakup of intensity into two pieces, the peak and the hump. So some of you, if you're familiar with cuprates, have heard of the peak dip hump, and most likely it's been in the context of the antinode. So let me remind you what that looks like and how this feature is interpreted at the antinode. So an important thing to mention before I get into this is that the antinodal peak dip hump is absent in single layer cuprates. So in Mercury 121 and other single layer cuprates, which have a lot of data from the antinode from ARPES, this feature is not seen. So it's a feature that is only seen in 2 and 3 layer materials, the antinode. So it is possible to get this entire line shape with one mechanism, but it's also common to interpret each piece separately. So let me go ahead and do that. So the peak part of the line shape is associated with superconductivity for the reasons that its intensity tracks the superfluid density, and also it disappears across TC. The dip feature is associated with mode coupling to some sharp excitation, either the B1G phonon or magnetic resonance mode. It is absent above TC, and for a given cut, it is momentum independent. And then finally, the hump feature, if it is associated with anything in its own right, it is associated with the pseudo gap because it does smoothly evolve into the pseudo gap above TC. So regarding the point over here regarding the momentum independence within a cut, let me go back and to one slide and show you what I mean in the context of whoops, wrong way. Okay. So in Mercury 1201, if we track just the dip position along a cut, it disperses along the cut, okay? So it seems to move to higher energies as you move towards the zone center. So this suggests that the dip is not a fundamental feature, but rather it's sort of just a coincidence of where the peak meets the hump. So we believe that the peak and the hump are the fundamental features, and then the dip is just the coincidence for the case of the nodal peak dip hump in single layer cuprates. All right, so going back here, this is the antinodal peak dip hump in multi-layer cuprates, and our phenomenology is somewhat different from that. So I mentioned the momentum dependence of the dip within a cut, which is different. And then there's the phenomenology otherwise. So in Mercury 1201, we see that the hump energy increases with underdoping, and it is a broad feature, and we define its energy from the peak of the broad maximum. So it is sort of, like I said, it's broad, but you can clearly see a difference between optimal and the underdoped specimens. The dip is present above TC. So this is different from the multi-layer cuprates at the antinode. And when we look at the momentum dependence of the hump, it seems to disperse to higher energies as we approach the antinode, and the energy scale that it extrapolates to at the antinode is comparable to energy scales that have been previously observed in optics at the same doping in Mercury 1201. Good. So there's a question in Figure C. How can we see the hump location? It seems confusing. Yeah, you're right. There's a lot of noise in the data. So the way that we ascertain the hump energy is that we smooth the crap out of the data, and we see where the first derivative is 0. So and then the error bars, which I don't have here, but we have them in the paper. They are found by taking the average of several adjacent EDCs. So this is kind of a subtle feature to pin down in energy. But for example, with this, for example, if you compare the blue curve and the red curve, for the blue, so let's start with the red, where let's compare orange to blue rather. So wherever the hump is for the orange, this is closer to the dip for the blue. So there's clearly some dispersion there. But again, this is a broad feature that is somewhat difficult to quantify precisely, and there is no precise quantification because it is so broad. All right. So the nodal peak dip hump, it has been discussed in other single layer cuprates. And oops. Specifically in sodium doped CCOC, it has been associated with polarons, lattice excitations that electrons drag around with them. And in bismuth 2201, it's been interpreted in terms of the lower band of the charge transfer gap. These explanations are not necessarily mutually exclusive. So just a reminder, cuprates, they're colloquially called Mott insulators, but they're actually charge transfer insulators. So what that means is that the energy scale, the energy penalty, I should say rather, for moving an electron from one copper to another copper is larger than the energy penalty for moving an electron from one oxygen to the adjacent copper. So the latter is the charge transfer energy scale, and because it is smaller, it sets the elementary excitations in the parent compound, and hence cuprates are charge transfer insulators. And as a corollary of that, this bottom part of the charge transfer gap, this bottom band of the charge transfer gap, actually reflects something about the correlated parent compound because it arises from the electronic correlations in this material. Similarly, the interpretation in terms of the polaron also takes into account correlations of the parent compound, but it introduces the lattice into that picture as well. So all of the interpretations of the nodal hump feature thus far have made references to the correlated parent compound in one way or another. So with one thing that where there is some materials dependence is that in bismuth 2201 and LSCO, the nodal peak dip hump structure does not appear at optimal doping, whereas in mercury 1201, we do see it at optimal doping as illustrated here. So this is something that I don't really want to make a big deal out of because it's perfectly possible that in bismuth 2201, the experimental conditions were just not optimized to see this feature, again, the matrix element effects. But it is also possible that maybe there's some intervening competing phase or some intervening phenomena that simultaneously suppress the nodal hump feature and also lower TC. So that being said, there are some materials differences, but there is a very intriguing universality that we see. So when we compare a number of different materials, there are some commonalities that show up and also some materials that are outliers. So in this graph, I have data looking at the hump position at KF at the node at low temperature for a number of different cuprates. And I'm going to first go through the outliers. So the first outlier is bismuth 2212, and this is the one that is the obvious outlier. So bismuth 2212 is a bilayer cuprate. Everything else here is single layer. So we don't necessarily expect it to behave the same way. But nevertheless, in the very underdoped regime, bismuth 2212 actually does show a nodal peak dip hump structure that seems to extrapolate to zero energy at around 8%, where a previously phase boundary associated with other phenomena in ARPES have been reported. So that's bismuth 2212. The other outlier is LSCO, where this hump energy as a function of doping does not appear to disperse. So this is something that is also understood. So it is thought that in LSCO, doping happens differently from other cuprates. So in LSCO, the chemical potential is filled, or it's pinned rather, and additional hole doping just piles density of states onto that pinned chemical potential, at least up to a certain point. Whereas in other cuprates, doping corresponds to a chemical potential shift, as we usually expect doping to do. So those are the two outliers. Now, if we consider the materials that behave similarly, we have bismuth 2201. sodium doped CCOC, and now mercury-1201 with data at higher dopings, all following very similar behavior, even quantitatively. And interestingly, when we take this hump energy scale and we extrapolate it to zero energy, it seems to extrapolate to zero energy right at the 19-20% point, which is a purported phase boundary of the pseudogap. So this is something that we don't have an explanation for necessarily at this point. I'm curious to see if you guys have any ideas, but it appears that that broadly speaking, this nodal hump feature is associated with some echoes of the correlated parent compound, both in terms of electronic correlations and lattice degrees of freedom that seem to collapse right when the pseudogap also collapses. So this is the last data slide I want to share, and I just want at this point to advertise a CMT search, condensed matter theory, that we have in UC Davis Physics, in case any of the people listening or any of your students are interested in joining this effort and others that we have in the department, or if you guys just really like spherical cows, we have those as well. And there's more details here, and this slide is on YouTube, of course. So this brings me to the conclusions. So from the data we have, we see 3 energy scales. So there's the low energy kink, which now we know from the new data is no longer only a feature of bismuth-based cuprates, and it likely originates from coupling to phonons that are in the charged reservoir layer. So it could be a window on the charged reservoir layer, although we haven't pursued that direction yet. The intermediate energy kink is something that is quite ubiquitous, and it is consistent in coupling to the softened portion of the bond stretching phonon. And the velocity renormalization across this kink is largest in mercury-1201 as compared to other single layer cuprates, suggesting that it is at least not bad for superconductivity. And finally, we have this nodal peak dip hump structure, which appears to be ubiquitous in single layer cuprates, and moreover with a common doping dependence with for many of the materials. And the hump is the feature that we focus on because it seems to echo the correlated parent compound, and it seems to collapse near the pseudogap endpoint. So beyond these results, something that I again want to emphasize as a challenge to the community is considering less commonly studied materials as an experimental path forward in cuprates. So one advantage here is one can access less explored doping regimes. So someone mentioned earlier the fact that thallium-221 is only overdoped. So that's an example of a less commonly explored doping regime. But another thing that people are starting to do now is looking at multi-layered, many multi-layered 3, 4, 5 cuprates with modern experimental technology. And there you can access the extremely underdoped regime without some of the disorder that often accompanies it in other cuprates. And also in this realm, there's the challenge of distinguishing universal versus technique-dependent phenomena, and universal phenomena versus phenomena that are very important to a specific material, but don't carry over as strongly to other materials. And again, everything I discussed today is in this preprint. I really appreciate the questions that you guys have had throughout this talk, and I'm happy to answer more questions now or talk offline at other times. Okay, so.
Thank you very much. Thank you, Ina, for the wonderful lecture, marathon talk. And I think we should hand her some water and blanket. She just finished. Any question from the audience? She should have time to drink, and then please ask and unmute yourself. Andre, I have a question.
Yeah, let me quickly ask a simple question. My soul, of course, is rushing to defend magnetic scenario for intermediate energy kink, but this will bring us 15 years back, and I will not do it. Let me ask a question about nodal peak deep hump structure.
Mhm.
You started by describing what is antinodal peak deep hump story. And then you said that peak is superconducting gap, and everyone agrees with this. Then you go to nodal region, and you said that peak and hump are fundamental. So question, what's fundamental about the peak in a nodal case when the gap is supposed to be 0?
So I guess what I mean by fundamental is basically that the peak is the energy it is, the hump is the energy it is, and their meeting point is the dip. So the dip doesn't reflect some sharp mode as it's often interpreted at the antinode. So
in this respect, do you expect that peak is just ARPES temperature variation or temperature reflection of the absence of the gap along nodal direction?
Yeah, so the peak at the node in Mercury 1201 and also other cuprates where it's been studied sort of more closely, it does not disappear across TC as it does in the antinode. Rather, there's kind of a smoother evolution, a smoother broadening as you raise the temperature of the node.
But is it temperature effect, the fact that the leading edge gap is 0, but the peak is still there, or you think it's fundamental, some energy scale which remains there even at 0 temperature?
So it is fundamental in a sense, but I'm not sure if it's important necessarily. So like, for example, if you measure a metal, if you measure a copper surface state and you look at the EDC at KF, you're going to see a peak. It's just something, a feature that has a well-defined energy. It doesn't necessarily mean it's associated with superconductivity or other orders somehow.
Okay.
So in the chat, there are some questions, and actually there was someone before Louis that I didn't get to. Let me scroll up. Okay, there was a question a little bit earlier. What is the effect of a shift in chemical potential, piling of density of states above chemical potential underdoping on the phenomena that are observed? Okay, so basically I think this is asking about the differences in how doping happens in LSCO versus other cuprates. And basically in most cuprates, doping appears to happen like we think of doping when you change the number of holes, chemical potential shifts. So if the lower band of the charge transfer gap is in the same place, the chemical potential kind of approaches that. The other scenario is realized in LSCO, at least in the doping range I showed, up to 20% or so, where the chemical potential appears to be fixed. And that assertion comes essentially from the fact that the lower band of the charge transfer gap doesn't appear to shift with doping. And the papers that I cited in that figure, some of them discuss this point directly for more information. Louis.
Yes, this was a wonderful talk. I really, really enjoyed it. Thank you very much. I have a few questions that maybe are a bit outside of the subject of your talk, but because this is really the first study, ARPES study of this particular material, and it's a material I'm very interested in. I'm curious, do you have any measures of the pseudo gap, its magnitude, its doping dependence, K dependence? Have you looked at the pseudo gap at all?
We have not. Something that is sort of I don't know if I mentioned it explicitly, but we found experimental conditions that optimize data near the node, and that's where we focus for now.
Right.
these experimental conditions do not optimize near the antinode. So we really don't have good information at the antinode. We have we've done other experiments at a different photon energy, which yields better, which has better cross section at the antinode, but it's a little bit too early to speculate. But there is sort of a lot of work that needs to be done there once experimental conditions are
that's
optimized.
very interesting. So in other words, you also can't say anything about Fermi arcs being present or not, and how long they would be, and so on, that sort of stuff.
No. So yeah, that information is not available in the data we presently have. I would say in the Bismuth 2212 data, there seems to be a lot of compelling evidence nowadays that Fermi arcs are just sort of a thermal artifact. So if you analyze data very carefully, you can see that there's still sort of a small gap there above TC. So essentially, there are a number of papers from the Dessau group and Kondo et al. That in various ways, and also from the Kaminsky group, that give evidence that nodes, that the point nodes actually exist above TC.
And a final quick question. One of the nice things you are able to do, which has been a matter of controversy in Mercury 1201, is to estimate the doping from the Fermi surface volume or area. Can you, I saw that for one of your samples. What is that? What are the 3 doping values that you actually studied from the Fermi surface area?
Yeah, so the nominal dopings that we have here are optimal, and then 2 underdoped ones, 11% and 9.5%. I do not recall what the ARPES values are for the experimental one. It can be kind of a tricky thing to measure as well, because we do not have information from the antinodes.
Okay, thanks. Thank you very much.
So there was another hand raised, Amaury Tremblay.
Yes, thank you very much, Ina, for this very nice talk. I have a question on your slide. It's called nodal PDH in other cuprates.
Yeah, let me, whoops, let me go back there. Oh, no, not this one, this one.
Yes, exactly. So, I mean, I'm not sure what is implied here. Do you imply that the U is equal to half an electron volt or order of magnitude? And why do you say that the hump comes from the lower band of the charge transfer gap, which means probably U, or I misunderstand what you're meaning?
So basically, this one that's colored in blue is the one that is attributed. And I think the energy position of this feature is broadly consistent with tunneling experiments in very underdoped samples, where they sort of see a rise so they see a gap that's asymmetric about 0, not like I've drawn it, and one where the density of states starts to rise at a comparable energy of half an eV or so on the negative side.
Okay, so that's really the charge transfer gap. Okay, thank you very much.
I think there's also one audience on Museo, Douglas. Is that right, Douglas Scalapio?
Yes.
Hello.
Thank you. Very beautiful talk. You really laid out the data for us. I have a question, which is, do you have any nodal data above TC?
Yes. Do you want me to go back there?
Let's see, I'm not sure everybody wants to go there. What I'm wondering is whether above TC you can see any structure in the 100 to 300 MeV regime?
Let's see. So that's not going to be present in the data that in the way that it's plotted, because it doesn't go to very high energy. But we do not see anything. We don't see changes in that energy regime across TC. So if they are very subtle changes, then we might miss them, because this is a more difficult compound to ARPES than some others. But the short answer is we don't see anything in those energy scales.
And so I could take that to be the same then as below TC. Is that fair? Or
yeah.
My point, I think, is I would expect the energies important for the superconductivity would be higher, and hence 100 to 300 MeV rather than down in the 10 or 50 MeV regime.
Mm-hmm.
And so I'd be very interested in what you see going on there as far as whatever is affecting the A of K omega.
Yeah, that's a fair question. So the nodal hump is kind of in that 100 to 300 MeV range. We don't see a tremendous change in that feature across TC.
Thank you.
Thank you, Douglas. Thank you, Ina. Any more questions from the audience? And comments or reference, whatever, are welcome.
So you guys feel free to reach out to me privately if you have comments or questions that you don't want to go public on YouTube. And I really want to thank you guys for all the questions that you did have, and thank you to Juven for putting together this really interesting program.
Okay, thank you. Thank you, everyone. Thank you, everyone. Thank you, Ina, for the pedagogical milestone talk. Just want to mention, we have this program website and also the upcoming speakers on the list on the website. Some of the people are invited, but not confirmed whether they will speak. In addition, if you know other experts or other people who are suitable to present, and please feel free to email me and inform me, and we can consider to add more people on the list. So that's all I want to say. And thank you again for coming to Ina's talk. And thank you, Ina.
Thank you very much. Beautiful talk. Thank you, Juven.
Thank you.
Thank you, everyone.
Very nice talk.
The talk should be available on the website and also on the YouTube soon. So stay tuned. Thank you.
Thanks, everyone. I'm going to head out now. Thanks, Juven, for the invitation and for being able to get so many people to come to a Zoom lecture.
Thank you very much. I'm sure there are more people that want to come, but they probably miss your talking.
Yeah.
All right. Thank you. Bye-bye.
Thank you.
Bye.